This is a conservation of energy example, the pulley. Here's the problem we're going to be looking at. A 5 kilogram pulley is made from a solid disc, 30 centimeters in radius, and has a lightweight string wrapped around it and attached to a hanging 1.5 kilogram mass. The mass and pulley begin at rest, but then the mass is allowed to fall. What is the speed of the hanging mass after it has fallen 2 meters? In the past, we've looked at a question like this, and we solved it using forces and torque. This time, we have a new tool. We can solve this using conservation of energy. The only force acting in the problem is the force of gravity, which is a conservative force. That means that energy is being transferred between categories, like gravitational potential energy and kinetic energy, but the total amount of energy is constant. So I can write that E initial is equal to E final. Initially, everything is at rest, and so there's no kinetic energy. But we can say that initially there is potential energy, gravitational potential energy. Compared to where everything ends up, the initial gravitational potential energy is equal to the hanging mass times the acceleration of gravity times its height above where it ends. The reason that we do not consider the mass of the pulley is that it does not change height. Its gravitational potential energy is constant through this whole problem. So as the mass falls, this initial gravitational potential energy is going to be converted into kinetic energy. But here we have to be careful. It goes two places. The gravitational potential energy goes into the falling kinetic energy of the hanging mass. So we'd write that as 1/2 times the hanging mass times its final speed squared plus rotational kinetic energy for the pulley. We write that as 1/2 I, that's moment of inertia of the pulley, times omega squared, and that's rotational speed. Now I'm going to solve this one symbolically, and then we'll put the numbers in based on the question. So the first thing I need to take note of is that omega has a relationship with V final, which is what I was asked to find. So omega is equal to negative V final divided by the radius of the pulley. The reason that there's a negative sign is because this hanging mass is hanging off of the left side of the pulley. So as the mass falls down, we would normally call that a negative velocity, and that is going to create a positive angular speed. And so there's a negative sign relationship between these. Of course, energy is actually a scalar. It's not a vector. And so we're going to be squaring omega and squaring our speed. And so that negative sign is going to end up not mattering, but it should be there nonetheless. So now this looks like, again, our initial energy is all gravitational potential, mg times delta y, equals, we still have the kinetic energy of the hanging mass, 1/2 mv final squared. Again, I'm solving for the final energy, plus 1/2, the I does not change, moment of inertia, but omega has changed. So I now have V final squared divided by the radius of the pulley squared. Alright, I was asked to solve for V final, and I noticed that on the right hand side I have V final squared twice. I can go ahead and factor that out. So now this is going to look like mg delta y is equal to V final squared. I can also factor out a 1/2 times m plus I over r squared. From here, I'm going to do a few algebraic steps just to clean this up and get a final equation in terms of v final equals. I'm going to multiply through by 2. That's going to eliminate this 1/2. So I'll multiply both sides by 2. I'd also like to multiply both sides by r squared because I do not like this fraction, which is going to end up in the denominator. So after I've multiplied everything through by 2 times r squared, then I will divide by this term in the brackets and take the square root, which will give me v final. So what this looks like at the very end is v final is equal to the square root of 2 times r squared, this comes from multiplying through, mg delta y, divided by, I'm going to have m r squared, that's from multiplying everything through by r squared, plus I. Alright, so here's the point in the solution that we came to on the last screen, that the final speed is equal to the square root of 2 times r squared times the hanging mass times the acceleration of gravity times the distance that it falls, divided by, in brackets, the hanging mass times the radius of the pulley squared plus the pulley's moment of inertia. So let's start figuring out what's going to go in here. Little m, the hanging mass, that was 1.5 kilograms. The radius of the pulley was 30 centimeters, which is 0.3 meters. Delta y is 2 meters. And moment of inertia, the problem specified that the pulley was made from a solid disk. The moment of inertia for a solid disk is equal to 1/2 the mass of the disk times the disk's radius squared. And in this case, that's 1/2 times 5 kilograms times 0.3 meters squared. For this pulley, the moment of inertia is equal to 0.225 kilogram meters squared. So this means that v final is going to be equal to the square root, let's leave a lot of room, 2 times 0.3 meters squared times 1.5 kilograms times 9.8 meters per second squared times 2 meters divided by 1.5 kilograms times 0.3 meters plus 0.225, and I'm not going to have room to write the units. They are kilograms times meters squared. So go ahead and run this through your calculator and we'll see if we get the same answer. So I calculate that the final speed of this hanging mass after it's fallen 2 meters should be 3.83 meters per second. With 2 sig figs, we should probably round this off to 3.8 meters per second. The problem asked for speed, and so this is sufficient, it's just the magnitude. If it had asked for a velocity, we would have to indicate that it was moving downward. But we have completed this problem, And I think it takes a lot less time to do this in terms of conservation of energy. You may want to try to solve it using forces and torques and see for yourself which method you think is easier.